Let me make one more important comment about adding vectors and thinking about Newton's law. Supposing we go back to that same example. So we have this hockey puck, and we've got those same force vectors, F1 and F2. And supposing that the puck was not originally at rest, imagine that it's cruising along with some initial velocity. What's going to happen? Newton's law tells you the answer. F equals ma. We just worked it out. I've just figured out the acceleration. The acceleration is up and right with a magnitude of 14 meters per second squared. But what's going to happen? It's got an initial velocity, and when you accelerate up and right, so here's an acceleration vector which is at 45 degrees, and you can't add velocities and accelerations, but remember, if the acceleration is constant, acceleration is delta v over delta t. So you multiply acceleration by time. If acceleration is constant, this is all safe. You get the change in the velocity vector. So the acceleration is acting in this direction. The change in the velocity vector must be pointing in that same direction. It's the same direction as the force. Initial velocity, change in velocity. Where's the final velocity? Well, there it is, initial plus change. Neither vi nor vf was pointing in the direction of the force. It's just something to be aware of when you're adding vectors. F equals ma tells you the direction of the acceleration. It's not necessarily the direction of the final motion, the final velocity. It's telling you not motion, but change in motion. So let me just summarize the central idea here. It's Newton's second law. F net equals to ma. So when you watch the Voyager spacecraft and you wonder to yourself, what's keeping it going? That's a bad thing to wonder. You don't need any force to keep an object in constant motion. If you have a zero net force, then you will have zero acceleration. That simply means no change. So Newton's law tells you about change in velocity, and that's what's interesting in life. Something's moving along, and you whack it, that's a force, and what does it do? It changes its motion. When you have this equation, you've got a beautiful description of everything you might care to know. If the force is constant, that means that you can deduce a constant acceleration. Now you can go back and use all our old kinematics formulas. If you know what the constant acceleration is, you can figure out position as a function of time and velocity as a function of time using kinematics equations. So that's one wonderful use of Newton's second law. I tell you what all the forces are. You need all of them, so you can figure out F net, and then you know the acceleration. That's a description of how it will change in motion, how its motion will behave as a function of time. Just so you know, Newton's second law is used in lots of ways besides that way. I don't always give you the forces and ask for the motion. Sometimes I watch an object and I measure x as a function of time. And then I say, aha, I know x, so kinematics tells me velocity and therefore acceleration. So I measure or observe the right-hand side. And I use Newton's second law to deduce what was the force acting on it. Maybe it was a force that was tough to measure. Maybe it was a hidden force like friction. I can figure out about new forces of nature by watching things move and using Newton's second law. Here's another way, just so you can see lots of examples of how you might use this equation. An astronaut's up in the space shuttle, and NASA's worried, is the astronaut getting skinnier? Are they sweating too much? Are they eating enough? They want to know what's the mass of the astronaut. How do you measure the mass of an astronaut who's floating around? You can't ask them to stand on a bathroom scale. A force meter just needs, you need some clever idea, and Newton's second law is the clever idea. The device that they use grabs the astronaut and shakes the astronaut. It shakes them with a certain predetermined motion, so you know what position as a function of time is, so you know what the acceleration vector is. And that little device has a force meter on it, just a scale. So you accelerate them and you measure the force, and you use Newton's second law to deduce their mass. Lots of examples, lots of different ways that we're going to use this equation. As long as you remember that it's a vector equation and that it's the net force that you want, this is the equation to use.